Hi everyone. So the purpose of this video is to go over the FRQs from your Unit 3 test. You're not turning these in for a grade, but I figured it would be nice to do a video showing you how to do the problems for your edification, and so you can work to improve yourself as you move forward. So we're given a function f and some values of it. Let me get on my, there we go, and of its derivative. And then the problem parts ask about functions that relate to f. So here we go. Part A, you're given a function, g of x, such that f of x squared minus 2x equals that. You're asked to write the equation of the tangent line. Well, in order to write the equation of a tangent line, you need two things. You need a point, so I want g of -1, and that will give me the y value on the function g. So I'm going to plug in -1 for the x's. That will give me f of 1 plus 2, which is 3. And then I can use the table. F of 3 is 7. So the point, -1, 7, is on the graph. And now we want to find the slope. Well, the slope is found by finding the derivative. And the derivative of g is going to require the chain rule. The outside function is f, so I'm going to do f prime. And then times the derivative of what's inside. Now that I've got the derivative, I want to plug in -1 again. This will give me the slope. So again, I get 3 on the inside, but it's f prime of 3 this time. And then at the end here, I get times -4. Well, f prime of 3 is 4. So my slope is -16. So now I'm going to use that, the slope and the point, to write the equation of the line. And any form will do. So that's part A. Now, part B. This was probably the hardest of the 4 parts, just because there's so much going on here. You're given a function h of x, and it's f of 3x over 4 times the square root of x all over e to the x. And you're asked to find h prime of 4. So we have a quotient rule, because this is a quotient, but the numerator is a product rule, and within that there's chain rule stuff going on. I know, it's diabolical, it's evil. So here I go, h prime. And I'm going to punt on a few of these just so you can see how this should look. So low, which would be e to the x, d high. That's going to require the product rule and the chain rule. Let me come back to that by punting. Minus high. Oops. D low. Derivative of e to the x is easy, so I'll just use e to the x again. Over low. And e to the x quantity squared, you could write e to the x with parentheses squared, or you can write e to the 2x. Those are the same. Now I want to address this, the thing I punted on. So I'm going to use the product rule, because that's the big rule here. So first, times the derivative of the square root of x, which would be x to the 1/2, bring the 1/2 down, reduce the power by 1, and you end up getting 1 over 2 root x, plus square root of x times the derivative of f of 3x over 4. So it's going to be chain rule. It's the derivative of f with the inside left alone. And then 3x over 4 is 3/4 x, so the derivative of that is just 3/4. Now, I could write out that entire derivative at this point, but I just need to remember to make sure that all of this was the derivative of e to the x. Sorry, was the derivative of the thing I just was, the stuff I circled in green. So when you put the e to the x out in front, there need to be parentheses around the green stuff. Instead of going through all that trouble though, I'm going to jump right in to plugging in my 4. So I'm going to have e to the 4th times, let's see, this would be f of 3 times 1 over 2 times the square root of 4, so that would be times 1 over 2 times 2, so times 1/4, plus square root of 4, which is 2, f prime of 3 times 3/4 minus f of 3 square root of 4 e to the 4th all over e to the 8th. So now, I've got e to the 4th. If I look back at the table, f of 3 was 7. So this is 7 times 1/4. And then 2 times 3/4 is 3/2, and f prime of 3 is 4, so 3/2 of 4 is 6. That's all that. Minus f of 3, which is 7, times 2, which is 14, times e to the 4th, all over e to the 8th. And one more thing I would do here, I have e to the 4th here, and an e to the 8th on bottom, so I really can simplify that. 7/4 plus 6, which I can combine, minus 14, all over e to the 4th. But quite frankly, at this point, you have a calculator, you should be plugging that in. I don't have the answer key in front of me, but the answer is, I think, it's a negative decimal that's bigger than -1. But whatever it is, you can calculate this from that point forward. Now, part C. Let me change colors here. So here, you're given a function that represents 3 times f of x plus 1 minus 4. And you're asked about, is there a place where m of c has to equal 0 in this interval? So this should look familiar to you. It's an intermediate value theorem problem. So the first thing we would want to see is if m is continuous. Well, f we were told is differentiable, and so it's also continuous. So any composition or transformation of a continuous function, as long as all the parts are continuous, is going to be continuous. So m is continuous. And whenever we're dealing with the intermediate value theorem, we always find the values of the endpoints. So I wanted to find m of -2 and m of 3. So when I plug in -2, f of -1 is -5. So that's -19. And then m of 3 would be 3 times f of 3 plus 1 minus 4. f of 4 is 1. Now, notice that the two y values I got are -19 and -1. And the question asks, is there a place where it has to equal 0? Well, 0 isn't between -19 and -1. So no, there doesn't have to be 1. Because 0 doesn't fall between -19 and -1. Now, if this had said m of c, is there a place where m of c has to equal -5? Absolutely, because -5 falls between -19 and -1, and by the intermediate value theorem, there would have to be a value that crossed it. And now, part D. Part D, you just needed to know how to take the derivative of an inverse. So w is the inverse function of f. The derivative of that is a formula we talked about, 1 over f prime of f inverse of x. And then when I plug in 3, what f inverse of 3 is saying is take a 3, look for a y value in f, and then tell me what x gave you that. So if you look at your table, the y value of is 3 when x is -2. So f inverse of 3 is -2, and then f prime of -2 is -6, and so the slope is -1/6. All right, let's talk about the second FRQ. So you're given a function here, and the first part is clearly an implicit differentiation part. So you're asked to show that dy dx is this. So we're going to take our function. It's not even, I don't even know if it's a function. I think it's just a relation. I'm going to take the derivative of it with respect to x. And every time I take the derivative of one of these things, I have to ask myself if the variable agrees with the x, and if it doesn't, I'll have to chain in a derivative. Now you can do this by switching it over to the Newton notation. I'm not going to do that here. So the derivative of x with respect to x is just 1. Derivative of, oops, sorry, that was an x squared, wasn't it? So let's make that the derivative of x squared with respect to x is 2x, and the derivative of what's inside, which is x, is 1. Derivative of 2x with respect to x is 2. The derivative of y to the 4th is 4y cubed, and the y doesn't agree with the x, so it's times dy dx. And then 4 times y, its derivative would be 4 dy dx. And the derivative of 5 is 0. So now we want to isolate the dy dx, so we would subtract all terms that don't have it over to the other side and factor out a dy dx. That would look like this. Divide both sides by 4y cubed plus 4, but I also think I'm looking at what the answer is supposed to look like, and I would probably go ahead and pull out a -2 from the top and a 4 from the bottom. And that would allow me to simplify this into something that looks like the answer. Like that. All right. For part B, write an equation for the line tangent to the curve at -2, 1. So we're already given a point. It's -2, 1. But we also need a slope. So we need to plug -2, 1 into the derivative in order to find the slope. So let's see, that would be -1, so that's 1 over 2 times 2, 4. So the slope is 1/4. So the equation of the line, ooh, pencil stopped working. Okay, I think it should be working now. So there is the equation of the tangent line. Now for part C, it says, find the coordinates at 2 points in the curve where the tangent line to the curve is vertical. So vertical means the slope is undefined. And the way a slope can be undefined is if the bottom is equal to 0, not the top. So things undefined when 2y cubed plus 1 is equal to 0. So I can solve that, get y cubed equals -1, which implies that y is -1. And then I want the x values. Now this is on the curve, so I want to go back and look at the actual curve equation and find what the x's are when y is -1. That factors, and the two numbers I get out of that are -4 and +2 as solutions, not as factors. So then my points are -4, -1, and 2, -1. And now part D. Is it possible for this curve to have a horizontal tangent line at points where it intersects the x-axis? So there's several ways you could approach this. The way I would approach this is to look at the two conditions separately and see if they're compatible. So first of all, curve to have a horizontal tangent. That means the slope is 0, which means in this fraction, the top equals 0, which means the x would equal -1. Okay, so from this derivative, The only way this can have a horizontal tangent is if the x value is -1. All right, so now let's look at the condition that it needs to be where it intersects the x-axis. So intersecting the x-axis means x-intercept, right? Which is where y equals 0. So I'm going to take my curve and let the y equal 0. So the condition that would give me an x-intercept is when this quadratic equals 0. Now, this means that we have an x-intercept. This means that the tangent line is horizontal. If I try to stick -1 in for the x over here, I'm going to get a statement that is not true. In fact, I think I'll get 1 minus 2 minus 5, which is -6 equals 0. Since this condition and this condition aren't compatible, no, it's not possible, because you can't have a horizontal tangent line at the same spot you're intersecting the x-axis.